Hey, see, a lot of us made it in. That's good. Today, um, hope you brought your umbrella because I think it's going to start raining before this class is over. See if I'm right, or shortly thereafter. Um, so we may not make it home. Uh, the question was about when can you apply calculus currency. Um, so the original plan was that you would do that at the end of the semester, according to the options in the syllabus. So I need to give you a form so that you can tell me how you want to apply your currency. Remember how that you get $15 for not violating the attendance policy. So that hasn't been factored in yet. Okay, and you need 25 altogether to replace if you want to replace your lowest score with the final exam. Okay, but there are lots of other options as well for the currency. What? Yeah, if you have 60, you can buy out of the final. Okay. Now there was another question: would we have any extra credit homeworks? I haven't put them here yet. I was thinking about that, but I haven't made the assignment yet. So I'll just have to see if I'm going to make the assignment. These are the homeworks, however, through the end of the semester. You will note that the semester dates have slightly adjusted. Okay, May 2nd was supposed to be the last class day. And then there were going to be reading days on May 3rd and 4th. I was told this morning, tentatively, but now I haven't got an email to this effect, so I may have to adjust these back, that the reading days on May 3rd and 4th would be canceled and used as makeup days, okay, because of the 2 flood days, okay? So that means then, if that's the case, then May 4th will be our last class day, okay, which is a Wednesday. That doesn't really affect us too much because the final exam is not until May the 11th in any case. So we were going to have a long gap there between that original last class day of May the 2nd and May the 11th, but I'm told that now the last class day will be May the 4th, okay? But again, that's what I was told, but I haven't gotten an official email to that effect, okay? So I did adjust the homework dates based on that, but now I may have to turn around and adjust them back if that's not the case. But anyway, these are the remaining homeworks that we'll have between now and the end of the semester. All right, so I pushed this one back. Homework 3.5 is due Monday. Sunday. Is that Sunday? I think that's a Sunday. Okay, so that's due Sunday at midnight, and that is about the product rule. Almost all of you finished the homework 3.4, so that's off the list now. That was due last night. So that one, and it looked like the scores were really good. So apparently, y'all were able to get through that. I've got the sample test for test number 3 ready, but I haven't posted that one yet. Okay. All right. So that's about where we are in terms of the homework. So Sunday night is your next due date, and we'll see what happens in terms of the semester days. Okay. Do y'all have any questions from homework 3.5? Some people have worked on it. About a third of y'all have worked on that. Do you have any particular questions on that, or other questions that you want to ask? Yes. On 3.5? Okay. Oh, that may be one that I think I know the one you're talking about. Maybe. Yes. Okay. I knew that was going to be an issue, so I've got a sample like that one, Zena, in my notes. So I'm going to show that right now in the notes, okay? Because I figured that one. It is actually easy, but when you're seeing it for the first time, it's a little bit confusing because it's not like it's not quite like the other problems. Okay. Are. All right. Other questions there? I have actually two examples, examples from this homework, like problems from this homework that I was going to work on. Okay. Other questions? So Sunday night is when this one is due, and I think it's very short. Oh yeah, there's only 6 problems, so that ought to be pretty easy. Okay. So I wouldn't wait until 11:30 on Sunday night, but it is pretty short, except there are multiple parts on some of these. That's always misleading when you see only 6 problems, because some of them have multiple parts to them. Okay. All right, so speaking of that, problem number 1, here's an example from the notes that I didn't get a chance to go over when we were talking about the product rule, like that problem. Okay, so here we've got some functions defined, but the formulas are not given to us. We're just told that we are given a function called f, all right, but we're not given its formula. And then we're told, well, f is a product of these two functions, g and h, but we're not given the formulas for g and h either, okay? But we are given some information about g and h and their rates of change evaluated at the input 2, and we're asked to find, to evaluate the rate of change, the derivative of the function f at the input 2, okay? So this is kind of an abstract example of the product rule, because you're going to apply the product rule, but you're not going to be able to find a formula for the rate of change of the function f to figure out what f prime of 2 is, okay, because we don't have the formulas for g and h. But nevertheless, by using the information that we're given and the product rule, we'll be able to answer this question fairly easily, okay? But we do have to remember the product rule, which says that in general, right, for any input, the rate of change at the input x, or f prime of x, is going to be, according to the product rule, right, that's going to be g prime of x times h of x, right? So you take the derivative of the first factor times the second factor, and then plus the first factor times the derivative of the second factor, right? That's how you use the product rule, okay, in general. So in this case, we're trying to determine what is f prime of 2. So we're just going to substitute the 2 for x in this expression, right? Even though we don't have the formulas for g and h, we can go ahead and substitute the 2 for x in this first equation. So we know that f prime of 2 would be g prime of 2 times h of 2 plus g of 2 times h prime of 2. And then that's where the information that we're given, you see, we're going to use, right? Because we're told what g prime of 2 is and what h of 2 is, and we're told what g of 2 is and what h prime of 2 is. So we will be able to figure out what f prime of 2 is, right, without actually, really doing very much at all, right? Okay, just substituting these values into this equation. So we know that f prime of 2 is going to be, let's see, g prime of 2 is minus 1, okay? H of 2, see, g prime of 2 we were given is minus 1. H of 2 is given to us as 4, so we'll plug that in. And then plus g of 2, we were given that as 3, so we can plug that in. And then h prime of 2, we were given that also. That is 0.5, right? So, see, we are going to use the product rule here kind of rather abstractly, right? Okay? We don't actually have to calculate any of these values because they're all just given to us directly. So let's see, what would this simplify to? Well, minus 1 times 4 is negative 4.
And then 3 times 0.5, I guess that's 1.5, right? That's half of 3. So you would have minus 4 plus 1.5, which turns out to be minus 2.5, right? Okay.
So you see, you can calculate f prime of 2 in this problem.
It's not really that fun to do it, but you can do it just using the information that you're given. Okay. All right. So that's like that, problem number 1. Okay.
So just write down the product rule as you know it, right? Okay. And then whatever value they're asking you to evaluate the derivative at, you just plug that in to the product rule, okay? And then they should have told you, given you all the information you need to simplify that. Okay, now let's look at one that's a little bit harder, though, okay? And y'all going to have to help me do some calculations. So if you've got your calculator or your phone or something here, here's an applied version of the product rule, okay?
So we have to read this problem.
And what it tells us. So it says the number of students enrolled full-time in fall in American public universities can be modeled by this formula, okay, where X is the elapsed year since 1999. Okay, so there's a problem with elapsed years again, okay? So when X is 0, for instance, that would exactly correspond to 1999. But you couldn't plug 0 in for X into this formula because natural log of 0 is undefined. Okay, if you try that in your calculator, you'll get an error. Okay, you can't calculate the natural log of 0. All right, but we're not going to try that anyway in this problem. All right, so this formula just gives us a prediction for the number of students enrolled in college, right? Okay, so that's what the function f does. On the other hand, now we have another function called t, okay, and this gives us a prediction of the amount of tuition that these students pay per student, okay? And this is in, obviously, you don't pay this small amount tuition, right? So this is in thousands of dollars. This is, this is not, this is in all public universities, right? Okay? Not just UH downtown, okay? So this might be, I don't know, above or below the tuition that students pay here, right? Okay? All right, so there's a formula for the tuition paid per student in thousands of dollars. And again, X here is elapsed years after 1999, okay? So the first thing we want to do there is kind of easy. We want to evaluate and interpret S of 16 and S prime of 16, all right? So did y'all write down the formula for S? Let me scroll back up here and where we can see that formula, all right? And so we want to determine first, what is S of 16, okay? What is S of 16? And what does it mean, all right? I'm not going to write down the interpretation, but because this is a very easy thing for us to interpret now. This would tell us, right, the number of students, right, enrolled in school, enrolled in college in what year? 2015, right, okay? Because remember, the input here is elapsed years after 1999, right? So to evaluate that, that's easy, right? That's just going to be 0.76 times the natural log of 16, right? And then plus 6.5, okay? So what is that calculation? What's the natural log of 16 times 0.76 plus the 6.5? Can you all do that for me? And we can round off to a couple of decimal places is fine, I think. 8.6.
8.607, so about 8.61 approximately. Does that sound right? Did y'all try that?
So if you're doing this on your calculator, calculate natural log of 16 first, then multiply it times the 0.76 next, and then take that value and add it to 6.5. That would be the correct order of operations on your calculator. So any disagreement with 8.61? Okay, so that tells us that according to this approximation anyway, in 2015, right, 16 years after 1999, there were 8.61 million students enrolled in public universities. Okay. All right. Now, the next thing we want to do, though, is calculate S prime of 16. Okay. And so that means, well, we're going to have to find the rate of change of S, right? And so we have to remember our derivative formulas now. Fortunately, this is a pretty simple formula, right, to find the rate of change for. Let's see, the rate of change of 6.5, that's a constant, so that's going to be 0, right? And what's the rate of change of the natural log of x? 1 over x, right? Okay, so we just end up here with 0.76 times 1 over x, right? I guess you could write that as 0.76 divided by x. There's the formula for the rate of change. And now we want to evaluate that at 16. Okay, so S prime of 16 is going to be 0.76, right, divided by 16. And what does that work out to be? Approximately going to be a pretty small number there. 0.048 maybe. Okay, 475. All right. So rounding to a couple of significant digits there, about 0.048. Okay. So what does that tell us then? Okay. That tells us then that that this number enrolled, right, is it going up or going down? Yeah, it's increasing by about 0.048 millions, okay? I don't know how much 0.048 millions is. That 48,000 per year, okay? In the year 2015, right? Remember, so that's in the year 2015. So in 2015, the number enrolled was going up by about 0.048 million per year, okay? All right. Remember, this is a rate of change, right? So it's telling us the rate at which this number is going up or down. In this case, it's going up because that's a positive rate of change. Okay, all right. So let's remember that because I think we're going to need that. All right. Now, this one is also pretty easy, okay? We just want to evaluate and interpret T of 16. So remember, T was for tuition. That was the amount of tuition paid per student. So T of 16, right, is just got to plug 16 into this formula. So we get the 0.19 times the 16, right, plus the 2.156. And what does that work out to be? 5.196. So that tells us that, I guess that's on average, right? Okay. Each student in the year 2015, right, at public universities was paying, that's $5,196 of tuition. All right. Okay. Remember, this is per student, right? So each student was paying there about $5,196 in the year 2015, right? Okay. Now, how was that tuition increasing or decreasing, as it were, in 2015? That's going to be T prime of 16, but T prime of 16 is very easy to calculate, right? Because this is a very simple formula to determine the rate of change for. What's the rate of change of T? Yeah, just 0.19, right? Okay, so just a very simple rate of change. And so that tells us that in the year 2015, right, that tuition per student was going up by 0.19 thousands, or I guess that's $190, okay? So in 2015, tuition per student was increasing by $190 per year, okay? Got two pers there, so that makes it a little bit confusing, right? Its tuition per student was increasing by $190, but that was each year. The tuition is increasing $190, okay? Because remember, our input here is elapsed years. All right, so when I go back and write down the notes, we will, I'll fill in these interpretations, okay? But I'm confident that you're good at making these interpretations now, okay? All right, so all that's just basic calculus. How are we going to use this, okay? All right, well, first, we want to write a formula for a function called f, which is the product of these two functions, s and t, right? So that's pretty easy to write down the formula for f if we don't simplify this product especially, right? Okay, so you're just going to take the formula for s, right, and then multiply it by the formula for t. Let's see, I remember the formula for t. That's 0.19x plus the 2.156, right? Okay, and then the formula for s was that, what, 0.76 times the natural log of x plus, what was that constant, 6.5? Did I say that right? 6.5? Okay, so there's a formula there for the product of s and t, okay? And I could simplify this by expanding this product, but I'm going to leave it in factored form because that's going to make it easier to use, I think, in just a moment when we're actually going to apply this function f, all right? So what is f really, before we go any further, what is f really telling me? You're taking the number of students, right? Okay? You're taking the number of students, and then you're multiplying it by the amount that each student is paying, right? Okay? And so that product is going to give you what?
Tuition, full-time student.
Yeah, it's the total tuition paid, right? Okay? So, yeah, this would be the number of students, right, times the amount that each student is paying, correct? Okay? So that would give you the total tuition paid by everyone, right, at American public universities. Okay? So that's what that product is, what that product function is telling you. Okay? What's a little bit tricky is the units of measure for the product. Okay, we'll have to think about that carefully. In just a second. Remember, this quantity is measured in what? Yeah, millions, and this was measured in thousands, right? So I guess our product here is going to be millions times thousands, right? And you have to think about what is a million times 1,000. What is a million times 1,000? Do you know the name of that number? I think that's a billion, isn't it? Yeah, okay. So a million times 1,000 is a billion. So I think this is going to give us billions of dollars paid in tuition, okay? All right. So that's what we're going to do next here is evaluate and interpret f of 16 and f prime of 16. But actually, we don't need the formula any longer to evaluate f of 16 or to evaluate f prime of 16 because we know what s of 16 was, right? We already calculated that. And we know what t of 16 is, right? So remember, the way we found the formula for the function f, it was s of x times t of x, okay? So f of 16 is just simply going to be s of 16 times t of 16. But fortunately, we already calculated s of 16 times t of 16, right?
Okay, we already calculated that. So what was S of 16? What did we find that to be just a moment ago? Did y'all write that down? 8 point what? 8.61. And T of 16 was 5.196. Okay. And so just multiply those two together, right? Okay. And that would give you F of 44 point what? 7376. So let's round that off to 74. Does that sound good? Okay. What's a dollar or two when you're talking about billions of dollars, right? Okay. So let's just round that off to 0.74. Okay. And so our interpretation is, right, in 2015, right, because this is the last year 16. So in 2015, right, the total tuition paid, right, for all students at public universities was 44.74.
Wait, it says for the T of X, it says thousands of dollars per student.
Yeah, thousands of, yeah. So this is thousands of dollars per student, right?
Yeah.
Okay, so each student pays about a little over $5,000, right? And this is the number of millions of students paying that tuition, correct? So all together there, you're going to get the total amount paid, right, by all students, okay? Because that's all students times what each one paid, right? So the total tuition paid, let me emphasize that, by all students at least according to our estimates, right, was, and then that was 44.74, okay, and it's billions of dollars, okay, because this is 1,000,000 times 1,000, and when you multiply 1,000,000 times 1,000, you get billions. Where did I get what now? The 8.61? We had already determined that a little while ago, remember? That was S of 16, okay? And that we got to be 8.61 from the formula for S, right? Okay? All right, so in 2015, right, okay, that's the total amount paid. But the next thing we want to figure out now is how was that total amount paid changing, right? Okay, so what was the rate of change for that total amount of tuition paid? That is what F prime of 16 is going to give us, okay? And again, one way you could do that is find the formula for F prime, and we could do that because we have the formula for F. But actually, we don't really have to stop and find the formula for F prime to calculate F prime of 16 because we have all the pieces that we need, right? Remember, F prime of 16, according to the product rule, that's going to be S prime of 16 times T of 16, and then plus S of 16 times T prime of 16. That's the product rule, right? Okay? See, remember F of X was S of X times T of X. So according to the product rule, you take the rate of change of S times T plus S times the rate of change of T. And you can just plug 16 directly into the formulas for S and T and S prime and T prime, right, to find this rate of change. And we've already calculated all of those. So let's see, what's this going to be approximately? What was our value for S prime of 16? I've forgotten. Was that 0.048?
Yeah.
0.048 there, plus T of 16 was, that's the 5.196, plus the S of 16 was 8.61, that's this, right, times the T prime of 16, remember that was very easy, that was 0.19, okay? And so now you just have all these calculations to do, right?
and you can find that.
Rate of change. So what does that work out to be? Someone who's fast with the calculator there. 1 point what?
88531.
So I'm going to say about 1.89.
Okay. All right. So approximately 1.89. I rounded off there to 2 decimal places. All right. So again, that tells us that. Wow, that's a big number. That's kind of discouraging, right? In 2015, right, the total amount of tuition paid was increasing, right, by 1.89 billion per year. Okay, wow. All right. Did someone else get that figure?
Yeah.
Okay. Okay. All right. Now, what is the actual formula then for f prime of x? So let's copy the formula for f so we can remember that. And then let's actually write down here. So there's the formula for f. So we didn't use the formula for f, right? We didn't use the formula for f, right, in finding f prime of 16, but we could have if we had written down the formula. So let's see what f prime of x is in general. So remember, according to the product rule, write this down first. It's s prime of x times t of x, right? So is that enough? All right, so it's s prime of x times t of x plus, and then s of x times t prime of x. So all we have to do is fill in what we previously found for s prime and t prime, right? So for s prime, let's see, we got, I think that was 0.76, right, over x, wasn't it? Times t of x, which was 0.19x plus, I forgot that constant. What was that constant as part of the formula for t? 2.156. 2.156? Okay. And then plus s, which was 0.76 times the natural log of x plus 6.5. And I'm almost going to run out of room, but fortunately I'm not, because, so that's s of x. And now we just have to fill in the rate of change of t, but that turned out to be really easy. That was just 0.19. So all that goes right there is 0.19. So there it is, okay? There's the kind of an ugly formula, right? Okay, but there it is, the formula for that product function. And in most cases, in the homework, you don't have to simplify these formulas, okay? So we could do a lot of simplifying here, expand these products and try to gather like terms and so forth, but in most cases, you're not required to do that, okay? So you can just leave it written like this. That's perfectly usable. A little bit clumsy, but perfectly usable formula there, all right? If you need to use that formula, okay? So there's a problem like this one. Not sure which problem it is in that product rule homework, okay? There's a problem similar to this problem. Okay. All right, so we're finished now learning rules for derivatives. We actually finished that last time. This is just a couple of more examples that I wanted to go through, okay? And let me save that. Well, that's going to take, that was a mistake. All right, there it goes. Okay, all right. And now let's continue with what we started just at the end of class last time, all right, where we're talking about not rate of change functions, but second rate of change functions, all right, and see how they are useful to us in applications. Okay. All right. So the second rate of change function, or the second derivative function, is the rate of change of the rate of change. Okay. So if you have a function and you calculate its rate of change function, well, that new function is just a function, okay? So you can also calculate its rate of change, and then you could calculate its rate of change and its rate of change and so on and so forth, okay? So you could actually do this indefinitely, all right? And in mathematics, actually, we do calculate rates of change of rates of change of rates of change of rates of change, okay? But in practice, in most applications, the second rate of change is where we stop, okay? All right? So that's where we're going to stop, is finding the rate of change of the rate of change function, and that's called the second derivative function. All right, so let's look at a formula here for a function. So I don't know what, I don't have an application for this one. I just made this up for this example. Okay, 2x cubed plus x squared minus 13x plus 6. And then let's find its second derivative. Okay, its second rate of change function. And then I'll show you how that is going to be useful to us in practice. Okay, we don't do this just for kicks, right? Okay, because we've had lots of practice calculating rate of change functions. I'll show you how we actually apply this knowledge of the second rate of change function. All right, so to find the second rate of change function, I don't think there's a shortcut here. There might be, but to find the second rate of change function, you have to sort of go through steps. So first you have to find the first rate of change function, right? Okay, and then once you found that, then you can find the second rate of change function. So you can't just jump, as far as I know, from the original function immediately to the second rate of change function. First you have to calculate just the rate of change. All right, but this is a fairly straightforward formula to calculate the rate of change function for. We don't have to apply any fancy rules like the chain rule or the product rule to find the rate of change of this particular formula. Let's see, what would it be there? So, yeah, that's right. So it's just going to be 6x squared, right? You're going to bring the 3 down, okay? And then plus 2 times x, you're going to bring the 2 down, and again, subtract 1 from the exponent there. And then for this third term, you'll just get minus 13, right? Because when you subtract 1 from that exponent, x to the first power, you get x to the 0th power, which is just 1. Okay? And the rate of change of the 6, of course, is 0 because that's a constant. So let's go ahead and multiply the 3 times the 2 there. So that gives us 6x squared plus 2x. All right? So that is the normal standard rate of change function. Okay? All right, to find the second derivative, you're just, pardon me, did I do it right? Oh, I'm missing the 13, yeah, okay. See, I was jumping ahead because that 13 is not going to last long, all right? Because what we are looking for is the second rate of change function, all right? Okay, which means we're going to now calculate the rate of change of 6x squared plus 2x minus 13. So we're just going to apply our rate of change formulas again, right? Okay, to calculate the rate of change of the rate of change. And again, that's called the second derivative, okay, which makes perfect sense, I guess. This is the first derivative, and now we're going to find the derivative of the derivative, which is called the second derivative. And the way we denote that is by just putting another prime here, okay, because this is a prime of the prime, so you get 2 apostrophes here to indicate the second derivative, the second rate of change function. Okay, but now you can just apply your knowledge of differentiation formulas again, right? Okay, so let's see. For the second rate of change formula, we're going to bring down that 2, right? Okay, and so that'll be 2 times 6x to the first power, and then for that second term, you're just going to end up with a 2. And then, like I was trying to do a moment ago, the minus 13 is going to disappear, right? Okay? So for the second rate of change function, you just get 12
12x plus 2. Okay? And again, for this class, we really don't look at this, but you can continue this process, okay? So you can find the third derivative as well. And what's the third derivative going to be here? Just plain old 12, right, okay? So you can continue this process indefinitely. It gets a little bit boring after the third derivative because the fourth derivative here, which is the rate of change of the third derivative, is just going to end up being 0. And then from then on, for this function, everything is just going to be 0, okay? So the higher order derivatives here eventually become 0, and so they get not too interesting, okay? All right, so, we're going to focus in this class on what does the second derivative tell us, okay? So what information do we derive from the second derivative? And what the second derivative tells us, as I'll explain here again, we looked at one example of this last time, but I'll show you with this function, again, why this is the case. Okay? What the second derivative gives us information about is the location of inflection points. Okay? So remember, the first derivative gives us information about turning points, okay, where a function is maximum or where a function is minimum. Okay? The second derivative, as it turns out, is going to give us information about where the inflection points are located on the graph of a function. And remember, an inflection point is where the concavity switches, okay, from concave up or concave down to the opposite, okay? So inflection point is where you have a change in the concavity. Remember, concavity tells you about the curvature of a graph, right? When a curve is concave down, right, it has kind of this hill shape, right? When a curve is concave up, it has this bowl shape. And the inflection point is where that switches, okay? The inflection point also, though, indicates to us where the graph is increasing the most rapidly or the least rapidly, or where it's decreasing the most rapidly or the least rapidly. I'll show you that in this example. Okay, so inflection point is where the concavity switches. Okay, but inflection point also tells us where a function is increasing most rapidly or least rapidly, or where it's decreasing most rapidly or least rapidly. So let's try that. Let's try that function that we were just looking at. Okay, the 2x cubed plus the x squared minus the 13x plus the 6, and let's see if we can find out the exact coordinates, not an estimate, but let's see if we can find the exact coordinates of the inflection points for this particular graph. Okay. All right, so I have a graph of this one already made, if I've done this right. There it is, okay? So there's the graph of 2x cubed plus x squared minus 13x plus 6, okay? And so what we want to figure out is not where the turning points are, okay? It does have two turning points, by the way, all right? So there's a turning point and there's a turning point. By the way, if you're looking for the turning points again, what helps you find the location of the turning points? That's the first derivative, okay? So the first derivative helps you find the location of those max values or min values, okay? That's what the first derivative is useful for, okay? And of course, that's very important, especially in applied problems, right? Because we're often looking for where the profit is maximum or where the cost is minimum, right? Okay? And first derivatives can help you locate those maximum points or minimum points. But the second derivative now, on the other hand, where that is useful is looking for inflection points. So that is where the curve is going to change concavity. And there is an inflection point. There must be an inflection point on this graph, right? There has to be an inflection point on this graph, because over here on the left, what's the shape of the graph? Is that concave up or concave down? Yeah, it's always easy to confuse the up and the down, right? Okay. This one is concave down. When it's bent down, okay, when it's bent down, right, so if you think of a straight line and you bend it down, okay, that's concave down, right? So this shape is concave down, all right? But over here on the right, you can see it switched. This part of the curve is concave up, okay? This part of the curve is concave up. If it looks like a parabola opening downward, that's concave down. If it looks like a parabola opening upward, that's concave up. So notice that we have switched from concave down to concave up. So that had to occur somewhere, right? Okay? And where that occurred is somewhere right in here. Okay, right? But you know, inflection points are a lot harder to find or to pick out than turning points are, right? I mean, the turning points are very obvious. There's a turning point right there, and there's a turning point right here. But where exactly is that inflection point? Okay, is it over here on the right side of the x-axis? Is it over here on the left side of the x-axis? Is it right there at 0? Where does that inflection point exactly occur? It's got to be somewhere right in here, right? Okay, I'm thinking. Okay, but exactly where, that's the tricky part. That's where the second derivative is going to give us information. Okay. All right. Now, let me show you why the second derivative helps you with that. Okay. All right. So I have also here typed in the formula for this is the first derivative. Okay. So I've got these a little bit out of order here. That's the first derivative. All right. And here is the second derivative. Did I write those down right? Yeah. Okay. Because that's what we just calculated just a moment ago. Okay. All right. So let's look at a graph there of there's the graph of the first derivative. Okay. So here's the original. So don't get mixed up by it's going to look a little bit like spaghetti here when you start plotting these things all together. Okay. But there's the original function. Okay, and the blue is the first derivative. Okay, notice now the first derivative there, right there, where the first derivative crosses the x-axis, right? Where the first derivative crosses the x-axis, that is where the first derivative is 0. That means it's right here where the tangent line for the original curve has slope 0, right? Because that's what the first derivative tells you. Notice that corresponds right to the turning point, and that's no accident. See, where the first derivative is 0, right there on the x-axis, that lines up exactly with the turning points on the original curve. So you see, that's why the first derivatives tell you where the turning points are on the original graph. Where the first derivative is 0, that tells you where the turning points are, okay, on the original graph, all right? But we're not looking for turning points here. We're looking for inflection point. Where right there is that inflection point, okay? All right, so here's another thing. Here's that second piece of information that I told you about inflection point. Inflection point tells you where a graph is increasing or decreasing the most rapidly or the least rapidly, okay? So look at this curve, right? Right here at this, see, we know there's an inflection point right here, right? Okay, somewhere right around there's got to be an inflection point. Of course, what's happening to the curve, the original curve, what's happening to the curve around this inflection point? Is it increasing or is it decreasing? It's decreasing, right? From left to right, it's decreasing. That inflection point is going to be right where the curve is steepest. Okay, right where the curve is decreasing the most rapidly, okay, that's where the inflection point is, okay? So you see it's decreasing right here, but the inflection point is where it's going down the fastest. So where the curve is the steepest, Okay. Now remember, what does the first derivative tell you? The first derivative tells you how fast a curve is increasing or decreasing, right? So we want to look for where the first derivative is the smallest. See, where is the first derivative the smallest? Because that is where the curve is going to be going down the fastest. There's the first derivative. So where is the first derivative the smallest? It's right here, isn't it? Right there? Yeah. See, that's where the first derivative is the lowest. It's down there below minus 10, right? That must be around minus 15 or something like that. Okay? That means right there, right about there, that's where the curve is going down the fastest, because that's where the first derivative is the smallest value. So I know that inflection point where the curve is dropping the fastest has to line up right with this turning point on the first derivative. It's got to be right about there. So you see, I already know a little bit better where the inflection point is. I know it's not on the right-hand side of the x-axis, right? It's got to be right there, close to 0, but not at 0, right? A little bit to the left of 0, okay? Well, that helps me a little bit. I know the inflection point is somewhere right about there, but I still don't know its exact value. That's where the second derivative is going to help you, okay? Because look, how do you find where that turning point is on the first derivative? You look for its derivative, right? What's the derivative of the derivative called? Begins with an S, what? The second derivative. So what we'll do is let's graph the second derivative and see where it's 0. Let's put in the graph of the second derivative there. Where is the second derivative 0? Right there, isn't it? Okay, there's where the second derivative is 0. That means that's where the first derivative has a turning point, where it's the lowest, and so that must be where this curve is dropping the fastest, right there at that point right there. Let me point at that and see if we can get a value for that. If Desmos will give me a value for that. Oh, it does. What does it say it is? Negative 0.167. That must be an estimate, right? Minus 0.167. So I know that inflection point is right there at minus 0.167. So it wasn't at 0. Okay, it was a little bit to the left of 0, right at minus 0.167. But how can I find that exactly? I don't have to rely on Desmos to give me an estimate. All I have to do is take the second derivative and set it to what? 0, right, yeah, okay. All I have to do is take the second derivative and set it to 0, and that will tell me exactly what that x-coordinate is right there, where that inflection point occurs, okay? All right, so let's do that. Is that making sense? I'm hearing a few yeses, okay? So I'm going to take that, to find that where that inflection point was exactly, I'm going to take that second derivative and set it to 0. Okay? So you see there's a really important parallel here. Okay? How do you find turning points? How do you look for turning points? You take the what derivative? The first derivative and you set it to what? 0, right, yeah. You take the first derivative and you set it to 0. Okay? That's where you look for turning points. How do you find inflection points? You take the second derivative, set that to 0. That's where you can look for inflection points. Okay? That's where you can look for inflection points. If you set the third derivative 0, what kind of point are you going to find? I have no idea. Okay? All right? Fortunately, we don't care about that. All right? So to find the location of the inflection points, possible location of the inflection points, you take the second derivative. What was that now? Was that 12x plus 2? And you set that to 0 and solve that equation. We better come up with something close to minus 0.167, I hope. Let's see. This gives us 12x is equal to minus 2, or x is equal to minus 2 divided by 12, which is minus 1/6, which if you type minus 1/6 into your calculator, you get minus 0.167. Yeah, okay.
So there is the x-coordinate of the inflection point, okay? It was minus 1/6. All right. Now, that's the x-coordinate. If you want to find the y-coordinate, you have to take this value and plug it back in, not to the second derivative. Don't plug it into the second derivative, because if you plug it into the second derivative, you'll get 0, okay? Take it and plug it back into the original formula. I'm not going to do that because that'll take me 15 minutes to calculate that, okay? But to find the y-coordinate of the inflection point, take the minus 1/6 and plug it back in to the original, formula, okay? Let's see if I can get Desmos is so friendly sometimes. Let's see if I can get Desmos to calculate that for me. So that was I wanted to know what f of what? Minus 1/6. So f of, let's see, minus 1 divided by 6. Oh, there it is. Okay. So there's f of minus 1/6. It's about 8.19 approximately. Okay. So about 8.19, that is the second coordinate of that inflection point. So we found it, you see, okay? Just by using the second derivative, we know there's an inflection point at minus 1/6 is the exact value for the x-coordinate, and for the y-coordinate, it's about 8.19, okay? That's where the concavity switches from, let's see, that was concave down to concave up, right? Right there at that point. So remember, at the first of the class, y'all were having to eyeball those inflection points, and that wasn't always easy to do. But now that we know, now that we have our knowledge of second derivatives, we can find the location of those inflection points exactly without having to guess at them. Let's try that again, okay? So let's find the coordinates of all the possible inflection points on this graph, okay? And then let's actually make the graph and verify that those really are inflection points. By the way, what we're getting ready to find initially here are just possible inflection points. Sometimes you can be fooled, okay? Sometimes points that are possible inflection points, they don't turn out to be actual inflection points, okay? So you have to always verify if your possible inflection point is really a true inflection point. And I'm going to do that just by making the graph, okay? Because you can see on the graph if a possible inflection point really is an inflection point. But first, let's find out where those possible inflection points are, okay? So how do you look for the possible inflection points? You're going to take the what? Which derivative? Yeah, the second, but of course to get to the second, you first have to do the first derivative, right? Okay? So you're going to end up taking both derivatives, but the one I'm concentrating on here is the second derivative. That's for inflection points. For turning points, you would use the first derivative, okay? All right, so let's find the second derivative here of this function f. So first, the first derivative, let's see, what's that going to be? 4 times 2 times x cubed, right? Minus 3 times 6 times x squared plus 4, right? Okay. So if we simplify that, that's 8x cubed minus 18x squared plus 4. That's the first derivative. So if you're looking for the turning points, you would set that formula to 0 and try to solve that equation. Ooh, that would be a formidable equation to solve, okay? So it might not be so easy to find the exact location of the turning points on this curve, okay? But fortunately, the second derivative is going to be a little bit easier formula. Let's see, what is the second derivative going to be? So, yeah, you're going to have 3 times 8x squared minus 2 times 18x, right?
okay? And then the 4 is going to go away. So we end up here with 24x squared minus 36x. And now I'm going to set that to 0, okay? Because that's where I look for the possible inflection points, by trying to solve this equation when I set the second derivative to 0. All right, let's see if we can solve this equation. Hopefully we can solve that by factoring. This is a quadratic equation, so we could use the quadratic formula, but maybe we can factor this one. I think we can, because from both coefficients there, you can factor out a 12. 12 goes into 24 and 36, and you can also factor out an x. Notice x you can factor out of both terms. So I'm going to factor out a 12x, and that will leave me with 2x minus 3. Is that right? So I have 12x times 2x minus 3 is equal to 0. And now I just set both of those factors to 0. So we have 12x equals 0 or 2x minus 3 equals 0. And those are real easy equations to solve. One solution is 0, because 12x times 0 means x has to be 0. And then this one is also easy to solve. Just add 3 to both sides and divide by 2. So we get x equals, not a bad value there, 3 halves. So it looks like we have a possible inflection point right at the origin. No, maybe not at the origin, but at x equals 0. Okay? And another possible inflection point at 3 halves. Okay? At x equals 3 halves. Notice this says find the coordinates. That means both coordinates of the inflection point. So to find both coordinates, you're going to have to plug 0 in to f. And you're also going to have to plug 3 halves into f. So plugging 0 into f, that's not so hard, okay? But plugging the 3 halves in is going to be kind of ugly. What's f of 0? Yeah, that's going to be 0, right? Because all those terms will become 0. So one possible inflection point is 0, 0. It is the origin, okay? X is 0, and y is also 0. I don't know quite what the second one is. That's 3 halves and whatever you get when you plug 3 halves into this formula. So that's going to be kind of ugly there, all right? So you probably need a calculator to help you find that second coordinate. We'll do that in just a second. All right. Let's verify that those possible inflection points really are inflection points. So we want to make a graph of 2x to the 4th minus 6x cubed plus 4x and see what we see. Okay. Does the concavity really change at 0, and does it really change at 3 halves? Okay. All right. So I've already got a graph of this one made, if I can find it. Is that the right function? Yeah, okay. So there's the graph, all right? And so do we really have inflection points where we thought we have inflection point? So there is the origin. Is that an inflection point? So does the concavity switch there at 0, 0? I think it does, because this is concave what direction? Up. And this part is concave down, right? So indeed, we have a switch right there at 0, 0. So 0, 0 is an inflection point, okay? Right? And where was the other possible inflection point? At x equal what? 3 halves, which is right here. Is that going to be an inflection point? I think so, right? Okay, there's x equal 3 halves, because right there it switches from concave what direction? Down to up, right. And that happens right there at that point, which is 3. Oh, that's very close to minus 4. I wonder if that is minus 4. Okay, it's very close to minus 4, all right, on the y-axis, but I'm not quite sure if that's exactly minus 4, okay. All right, so indeed, that second possible inflection point is an inflection point. Let's have Desmos calculate what f of 3 halves is. So I can just type that in. F of 3 divided by 2. And it's not quite minus 4, but it's really close. It's minus 4.2. 4.125. Okay? So let's fill that into my notes. Minus 4.125. Okay? There is the second inflection point. That was f of 3/2 was minus 4.125. And those are both inflection points, okay? Because we checked them, and we could see that the concavity really did switch there at those inflection points. All right. Now, I've got one more question. For both of those two inflection points, I want you to decide what's the case here. At that inflection point, is the function increasing most rapidly, or is it increasing least rapidly there? Or is it decreasing most rapidly or decreasing least rapidly at that inflection point? Okay? So let's look at the graph and see if we can decide which is the case here. Increasing most or least rapidly, or decreasing most or least rapidly at that point. Okay? All right, so let's look at Desmos. There's the first inflection point. So we can see right there that definitely the curve, is it going up or is it going down?
Well, it's going up, though.
Yeah, it's going up, right. It's increasing, but is it increasing the fastest right there, or is it increasing the slowest right there at 0, 0? Okay, that's fastest right. Think about what's happening as you're going from left to right. First, it's not increasing at all, right? Okay? And then as you go from left to right, it starts increasing more and more and more and more and more until right there, that it's not increasing very rapidly right there, but that's where it's increasing the fastest. And then it starts slowing down how fast it's increasing. And in fact, right there, it starts to peak out, right? Okay? So right there at this inflection point, it's increasing the fastest, all right? What about this inflection point? Is it going up or going down? It's decreasing, and is it decreasing the fastest or the slowest right there? That's the fastest, right? That's where the curve is the steepest, going down. So it's decreasing the most rapidly. It's a little bit a contradiction, it sounds like, right? But decreasing most rapidly right here at this inflection point. See, it's decreasing, and then it really is going down fast, very steep right there, and then it's still decreasing, but it's not decreasing as rapidly as you move to the left, to the right of that inflection point. Okay? All right, so so increasing most rapidly, decreasing most rapidly. Let's put that in. So let's see, increasing most rapidly, that's I, and decreasing most rapidly is I. So this one is I, right? Increasing most rapidly, and at this inflection point, it was decreasing the most rapidly right there. Okay? That was the behavior of the curve. And we can see that by looking at the graph. Okay, we got a few minutes here to practice a few second derivatives, so let's try this, okay? All right, so let's see if we can get a couple of these done. These are all really pretty straightforward, okay? All right, so I want you to find now the second derivative there of each of these formulas. Let's start with the first one, though, with A, okay? So find the second derivative of A, all right? And remember, you got to find the first derivative first, okay, before you can find the second derivative. All right, so try that. We'll take a minute or two. That one's pretty easy, so that one shouldn't take long. So try this now. So when you're doing your homework 4.4, this is homework 4.4. Believe it or not, we're already for homework 4.4. Okay. You'll have a little prior practice. While y'all are doing that, let me see if I got an email about the... I do have some emails here. Yeah. Y'all have to come May the 4th. I'm sorry. We just don't want to cheat you out of anything you paid in all that billions of dollars of tuition, you know. Okay. All right, so let's see. What is the first derivative here? Because we need that to find the second derivative, so that should be pretty easy. That's just what? 6x minus 7, right. So the second derivative is so easy. That's just what? 6, exactly. All right. So there you get a constant second derivative. It's going to be 6. By the way, that tells you that this curve has no inflection points because there's no way 6 is ever going to be equal to 0. Okay. So the second derivative can never be 0 because it's always 6. And so that means this curve has no inflection points, all right, on it. It doesn't ever switch from concave up to concave down or vice versa. It's either one or the other everywhere, okay? All right, let's try the second one. Got just enough time to do the second one. The third one's very similar. C is very similar. So try the second derivative there. I have a few more examples in here, but we'll finish those up on Monday. And then we're going to do something completely different. Well, it's going to seem like it's completely different, but it turns out in practice to not really be as so different as it seems. All right, so did y'all get that yet? What is the first derivative of g? Negative 6.3x squared plus 7x plus 7. Okay. And then what is the second rate of change? Yeah, minus 12.6x plus 7, right. So it's possible that that curve does have an inflection point because, indeed, you can set that to 0 and find a solution to that equation, right? It's going to be an ugly solution, but it's there, okay? So it's maybe this curve, when we graph it, will have an inflection point. This one doesn't, but maybe this one does, wherever the solution to that equation is, okay? We'll see if we can look at that next time and see where that inflection point actually is. Okay, all right, so homework 3.4, is it 3.4? No, 3.5, yeah. 3.5 is due Sunday night, okay? I think that one's pretty easy. So you can now continue working on the other homeworks too, okay?